Hello, my name is Daniel Frisch. I'm at the Intelligent Sensor Actuator Systems Laboratory, ISAS, with Professor Uwe Hanebeck at the KIT in Karlsruhe in Germany. And my talk in the Advanced Nonlinear Filtering 1 session of the conference Fusion 2020 will be about progressive Bayesian filtering with coupled Gaussian mixture and Dirac mixture densities. The first input argument we need for our method is the prior, given as a Gaussian mixture density. Here we can see a single Gaussian for visualization, but it could be Gaussian mixture as well. Second input argument is the likelihood function. Here we have a distance measurement, so it's a nonlinear subspace measurement. And this area contains the 2 sigma bounds of the additive noise. Additive noise is not a requirement here. It could be any kind of noise as long as we can state a numeric function handle of the likelihood function that can be evaluated anywhere during runtime. And our method now transforms these inputs into a Gaussian mixture approximation of the posterior density. Here this would be the ground truth by multiplying these 2 functions, and this is our Gaussian mixture approximation. The methods we use for this include the progressive update that we will also focus on in this talk from now on. Additionally, under the hood, we use the expectation-maximization algorithm and deterministic Gaussian sampling that is based on the localized cumulative distribution LCD and a modified Kramer von Mises distance. So here's a quick recap of the Bayes rule. Suppose we have a 2-dimensional state space here, x1, x2, and this nonlinear measurement function that produces a scalar nonlinear output. Also we have additive noise, for example, and then during runtime we get one measurement, and the likelihood function includes all the information from the measurement model and the measurement. Additionally, to the likelihood, we have the prior density that includes the information from the previous measurements made in the past and the system model, the state transition model. And we want to fuse these types of information, and according to Bayes' rule, we do this by just multiplying the likelihood function and the prior density, renormalizing it, and this is our wanted posterior density. We can, of course, easily pointwise multiply any prior Gaussian mixture density with an arbitrary likelihood function, but as we know, the result is not necessarily Gaussian mixture anymore, and then we may run into problems solving the Chapman-Kolmogorov equation during the next update step. Therefore, for nonlinear filters, we usually use sampling, like this random sampling of a Gaussian. We could also use the unscented Kalman filter sampling that is moment-based. If we want to get more precise, we can select more samples on the principal axis. This is also easy. And when we want to get even more precise and also cover these areas apart from the principal axis, we can use deterministic Gaussian sampling based on the localized cumulative distribution. This is more precise for the same number of samples than random sampling, so this is what we use in our proposed filter here. When we take samples of the prior, then the information of the prior is encoded in these sample locations that are equally weighted in the beginning. And then we might think that we can already solve the problem by just reweighting those samples with the likelihood function value at their respective sample location. This would be kind of a multiplication according to Bayes' rule. Then the likelihood information would be encoded in the weights of these samples. And together these reweighted samples with sample locations and sample weights would be the fused result of the posterior. But in this example we can see that most samples would be reweighted by 0, so much information gets lost and we have to expect a bad filter result for this naive approach. Let's look into this sample degeneration problem and see how we can deal with it. So these vertical black lines are our sample locations. This is our original likelihood, and we can see the problem is that the likelihood is too steep. These samples here on the right are basically reweighted by 0. But what about when we don't take the original likelihood, but the square root of the likelihood? Then we get a function that is already smoother. And when we take exponents of the likelihood that are even smaller than 0.5, we get smoother and smoother or flatter versions of the likelihood. As here for this purple one, we see that nearly all samples get really non-zero weights. The extreme case, of course, when we take the likelihood to the power of 0, then it's too flat, but we need to find some intermediate optimal value of the likelihood exponent that fits to the samples, such that we avoid sample degeneration. To formalize this, we plug it back into Bayes' rule. Here's again Bayes' rule, constant times prior times likelihood. And when we use the flattened version of the likelihood, like the square root, but we perform 2 successive update steps with that, then we see that overall we have done the same update step as in this case. We also call this flattened likelihood version sub-likelihood. And more generally, we can use arbitrary exponents of the likelihood. Then we have to perform r successive update steps, such that the sum of likelihood exponents equals to 1. Then also we have formally done the same update step as in this case. Here comes a detailed graphical example where we can visualize all the intermediate steps. This is the likelihood function visualized by the 2 sigma contour lines of the additive noise. This is the prior Gaussian, could be also Gaussian mixture, and the first step is to obtain deterministic samples of the prior. If we would now reweight the prior samples by the original likelihood function value, then we would face severe sample degeneration because the likelihood function is close to 0 here. Instead, we use a flattened version of the likelihood with a likelihood exponent of 0.05. In this case, the weights of the samples are much more homogeneous. And now we use the expectation-maximization algorithm to approximate this Dirac mixture of weighted samples with a Gaussian mixture. When I now switch to the next slide, you will see that this gray line becomes the new yellow line, because the last sub-posterior is the new sub-prior for the next progression step. Here we use another flattened version of the likelihood with an exponent of 0.1, and we can see that the shape of the new second posterior after the second progression step is already closer to the shape that we expect in the end, and also the samples are traveling into the direction where we need them. Here is everything again in one single picture: the yellow prior from the beginning, the 2 gray intermediate results, and the red final estimation of the posterior. The ground truth is indicated in black here. On the past slides, we focused on contour line plots for better visualization, and the final result is also indicated as a real density function here. This is the ground truth, and this is the Gaussian mixture approximation as a real density plot. In summary, we work with a Gaussian mixture and a Dirac mixture that are coupled together. We start with a Gaussian mixture prior, we draw samples from that, then we reweight the samples in a Bayesian way with a flattened version of the likelihood, then we reapproximate that weighted point cloud by the expectation maximization algorithm with a new Gaussian mixture. And we repeat these steps until the sum of these likelihood exponents are equal to 1. Of course, during that process we make some sampling errors, reapproximation errors in every step, so we want to keep the number of steps as small as possible. In this little evaluation, we will brute force all possible variations of likelihood exponents for up to 3 progression steps. So this axis indicates the first likelihood exponent. If it's 1, then the other 2 are 0. But otherwise we have to select the second likelihood exponent as well. And then the third likelihood exponent is just 1 minus the other 2. The color here indicates the L2 norm between ground truth and Gaussian mixture approximation of the posterior density. So blue means bad, yellow means good estimation result. And for example, when we select the first likelihood exponent to 1, That means that we don't use the flattened likelihood, we don't use the progressive update, then the result is pretty bad. Instead, the sweet spot is around here, when we select the first likelihood exponent very, very small, the second likelihood exponent around 0.1, 0.2, and cover the rest with the third likelihood exponent. We come to the conclusion now. We presented a novel algorithm for nonlinear Bayesian filtering, the update step, and it's pretty universally applicable as it can handle Gaussian mixture priors or Dirac mixture priors as well, and the likelihood function can be given as an arbitrary numeric function handle. Application scenarios include multimodal setups, where a normal Gaussian estimator is not adequate anymore, and also these cases of non-overlapping prior and likelihood, where I otherwise would need a huge amount of samples. In the future, we want to improve the expectation-maximization algorithm such that it can adapt the number of Gaussian mixture components to the current requirements and improve the handling of degenerated Gaussian mixture components and change the stopping criterions of the expectation maximization algorithms. For the progressive update, we want to compare different choices of the likelihood exponent during runtime and also improve the Gaussian sampling scheme. Thank you very much for watching.